All right, guys, so in this video we're going to review some of our integral concepts and applications. First one we'll look at is finding area between curves. You could do this with respect to x, or you could do this with respect to y. Now when it comes to doing it with respect to x, you have your two functions. We'll say that this one here is f of x, and we'll say that this one here is g of x. Okay. Let's go ahead and we'll call this point here, we'll call that AB, and we'll call this point up here CD. Okay. So now, if you want to find the area between the curves, in other words, this shaded area right here, then what you're going to do is you're going to integrate, where you do the top function. Actually, I'll just go ahead and put f of x minus the bottom function. But I will write underneath here, top minus bottom. And that's with respect to x. And when you're integrating with respect to x, the x value on the left goes here, and the x value on the right goes here. Okay? And that's how you can find the area between the curves. Now, if you wanted to do it with respect to y, a couple of changes need to take place. First of all, your equations have to be in terms of y instead of in terms of x. We'll use the same letters and points here. Now in this case, if you wanted to find the area between the curves, which is the same region, not only do your functions need to be in terms of y, but when you're integrating with respect to y, you're going to put your first y value, which is b, on the bottom, and your highest y value, which is d, on the top. So it's the y values for the limits instead of the x values. And second of all, it's not top minus bottom, but it's right minus left. And in this case, the g function is farther to the right than the f function is. So this one would be g minus f because it's right minus left. Okay? And so that's how you can find area between curves. Let's go ahead and take a look at our next slide. So this is a question where we're asking you to find the volume of a solid with a known cross section. Okay? Now usually what they're going to do is they're going to give you some kind of an area. So let's say it was just this half circle here. They're going to call that the base. And what they're going to tell you is that they're going to be stacking some kind of a shape on here so that the shape's base is perpendicular to either the x or the y axis. So let's start off with doing one with the x axis. So I always like to draw a flattened version of the graph. And there's my base, right? Now let's say I wanted to stack on top of there a square so that the square's base is perpendicular to the x-axis. Well, that would look like this if I'm perpendicular to the x-axis, right? So there's the base of my square, and then the square would look like that because it's coming up into the three-dimensional world. Okay? So there's that. We're going to say that this is called the cross section. Okay. Now, the way that these things work is you're going to be integrating the area of your cross section from beginning to end. I'll call it x1 and x2. with respect to x. And that's pretty much it. And what that does is that allows you to stack an infinite number of these shapes on there, and you end up with some kind of a volume. Okay? So that's only one square that I've drawn in the middle section up there. But if you were to put an infinite number of those squares on there where the base is always the distance between your function and the x-axis, and stack them all together, you're going to end up with a solid figure, and its volume would be found in that way. Now, in the same way, you can have things be done with respect to y. So this is, over here, this is perpendicular to the x-axis. Okay? I'll call this base up here, well, not the base, I'm sorry, we'll call the base, the curve is f of x. And the area of the under the curve is the base, right? Okay, so now that's perpendicular to the x-axis, but you can also do these problems so that they are perpendicular to the y-axis. Okay, so let's see what that would look like. So for these types of problems, once again, you're going to have a curve. Let's go ahead and we'll call this one. I'll just do half of a circle here. I'll do that. Well, I guess we could do a full circle. Why not? Right? We better do a half. We better do a half because otherwise it's going to overcomplicate things. We'll do a half circle. All right. And so we want to find the area of our base. Now the difference here is if I'm doing it perpendicular to the y-axis, then my shapes are going to be stacked on there going in this direction. That's horizontally. And when that's happening, our function has to be in terms of y instead. Okay? Now let's go ahead and look at our three-dimensional view of this. Don't want red. There we go. And that's the base of my square. Now my square would get stacked on it like this. Okay, so that's the difference there. And in those cases, the volume is going to be found by integrating from y1 to y2 instead of x values or y values. So you're integrating from bottom to top instead. And you're still going to put the area of your cross section here. So in this case, it's a square. And that's this thing. That's my cross section. And we're going to be integrating with respect to y. Okay? So you could, if you want a perpendicular y-axis, you do it that way. X-axis, you do it the way on the left. Okay? Now, the most common types that you'll see on the AP exam, common cross sections, include the following things. You have a square, you have rectangles, and right triangles. They do these ones because these are ones that they expect you to already know how to find the area. Like you know how to find the area of a square, you know how to find the area of a rectangle, and a right triangle is just the same. It's just base times height cut in half. So they'll give you these types of problems most likely. In class, we talked about semicircles and equilateral triangles as well, but those are a little bit less common just because the formulas for the area are not as common. So people don't just know them off the top of their head. And so these are the ones you can expect to see for the areas of your cross sections. Okay? But anyway, that being said, let's go ahead and move on to our next topic, rotations. Now you could create a volume by rotating an area around an axis. There are two types. There's the disk method, and then there is the washer method. The only difference is that disks have no gaps, so you end up with a solid figure, whereas a washer has gaps. And so you end up with a hollowed figure. Okay, so for instance, if I had this shape here and I was rotating it around the x-axis, there would be no holes or gaps in that shape, and you would have the disk method. And the way that that would work would simply be you go from your first x value to your last x value, and it's going to be pi times the radius squared, where the radius is this function here and its distance from the axis. So g of x minus the axis, and there's that. Now, the washer method is if you have a gap. So let's say that I want to rotate it around the same axis here, the x-axis, but let's say that my shape was up here now. Okay, well, I'm going to think of this as a new function. We'll call it g, and I'll think of this one up here as another function which we'll call f. Now in those cases, it's going to be like you're going to do the f function minus the axis squared minus g minus the axis squared. Okay. So what goes here is the one that's farthest away from your axis. Okay. And this one is the one that's closer to your axis. Okay, so G is closer to the axis I'm rotating around than F. Now I notice that a lot of you guys on your work, when you did this, you put your pi inside. That's so long as you have these brackets like I do, it's okay to put it like right here. But some of you guys didn't have those brackets, and so you put your pi right here without brackets, and that means you're only putting the pi on this F, and you're going to get the wrong answer. So the best thing to do is just to go ahead and put the pi out here, and you can avoid that issue. Okay, because the pi actually applies to the whole thing, not just the first one. Okay, so that is that. Now, of course, this can be done with respect to y. So these are for horizontal axes of rotation. But of course, we could do all this with vertical axes as well. And in those cases, you're going to be doing everything with respect to y. So the same principles apply. Disk method has no gaps. Washer does. The radius of the circle of rotation is just the function minus the axis. You square that and do pi with an integral with respect to y, not with respect to x. And that's the disk. Now for the washer, instead of one that's, well, actually the same principle applies. It's still the one that's farthest away from the axis. So in this case, the F is farther away from the axis of rotation than the G. So I put the F minus the axis first. Okay. Now once again, to do this strategy, you have to have your equations are in terms of y. So it's F of y, and this one would be G of y. Okay, so that's important. Anytime you're doing an integration with respect to y, your equations need to be in terms of y, and your limits are y values. So that is volumes of rotation. What else can we talk about with integrals, concepts, and applications? Net change. So what is net change? Well, the integral of some kind of a rate function, we'll call it f prime, on an interval, let's say a to b. If you integrate a derivative on an interval, what that will tell you is the total change in f on that interval. So let me explain that with an example. So let's say that f prime of x is some kind of a rate, like speed of a vehicle. So we'll say miles per hour. I'll say velocity to be more specific. So let's say that f prime is going to be modeled by something like that. Well, if I were to integrate f prime on the interval from a to b, what that's going to tell me is the total change in f. So the starting value of f minus the ending value of f, actually I said that backwards, ending value of f minus starting value of f, that's the total change in f. Now what would that be though? In this case that would be the position of the vehicle, its final position minus its starting position. So for instance, if my car is traveling at a rate of 50 miles per hour and I integrate that rate on the interval from a to b, basically it's going to tell me the distance that my car traveled, or its actually in this case a more formal word would be displacement, but it's okay to think of this as a distance in this case. But there's the idea. So whatever unit is on the top, that's what f is. So f is in miles. So after you integrate this, you end up with a certain number of miles that you traveled. Okay? And so that's what net change is. The integral of a derivative tells you the total change in f on that interval. The average value of a function is found by adding together all the y value. Actually, we should say this. It's the average y value or height of a function. And we know how to find averages. You add together all the things and divide by how many there are. But in calculus, the way that you add together all the y values is you integrate your function on the interval. And the way that we're going to divide by how many there are is we divide it by the length of the interval. And so there's that. That will tell you the average y value or the average height of your function. Go ahead and take a look at another topic here. Properties of integrals. We talked about 6 different properties in this class. So let's go ahead and go through those real quick. So one of the properties we talked about is that if you're integrating a function from a to b, you're allowed to reverse those integrals, which sometimes we do want to, or those limits. We're allowed to reverse those so long as we put a negative in front of it. Okay, so that's one of our properties that we learned. Another property that we learned was that anytime you're going from a to a, that's just going to be 0. It means you don't have any length to this interval, so there's no area, therefore you're going to get 0. Another property is that if you're adding together 2 functions, you could just take the integral of each one separately. Put my dx's in there, I guess. So there's that one. Another property that we have is a constant multiple property. So if you have a function that's being multiplied by a constant, a number, it can't be a variable, it's got to be a number, then you can rewrite that where the constant's just outside of the integral. I guess I should probably use different letters than A, so we don't get confused there. All right. Another property that we talked about was this one. This one's pretty popular because it's the one that makes you think the most. So if you're integrating some function from a to b, and you want to add that to a function from the same, integrating the same function, but from b to c, notice that this function leaves off where this one picks up. And therefore, you could really just put those together as A to C. But they have to be connected at the B there. That was pretty popular. And the way it usually works is they'll give you two of these. It could be these two, or it could be these two. You don't know, but they'll give you two of them, and they'll ask you basically to solve for the third one. So you want to get your setup going on here, and after you get your setup, just plug in what you know and solve. The last thing is if you're integrating a constant. If there's just a number there and there's no letters, then basically this integral will be equal to A multiplied by this, the top minus bottom. The top limit minus the bottom limit. Okay? So those are our properties of integrals. Let's talk about the second fundamental theorem of calculus. Now we have the basic one. Okay, and here it is. If you have an integral where you have a number on the bottom, matter of fact, I'm just going to go ahead and put number here. It has to be a number on the bottom. And if just an x on the top. We don't really care about what variable's inside the integral. But if you have this, and you want to take the derivative of this with respect to x, then what's going to happen is two things. The integral is going to go away, and the x is going to replace the t. And so you end up with this. That's the second fundamental theorem of calculus. Okay? Now, you could have a more complex one. Okay? So what that would look like is, instead of having a number down here and just an x here, it's possible you could have more than that. In fact, you could have a function here and a function here. Now, if you wanted to take the derivative of this thing, the way this one works is basically, now this is a little bit complicated. I don't think I want to go too much into the explanation, but I'll kind of give you a brief little overview. So typically you would integrate this and it would give you an integral, right? But we don't know what the integral of little f is there. But it doesn't matter. We're going to take the derivative of it, which is going to cancel it. So it's just going to go back to being f, right? But we're plugging in h of x. We also need to plug in the g of x, and so you subtract them. But since we're taking the derivative, the chain rule would have you take the derivative of the inside here. So you're also going to multiply it by the derivative of h on that one, and on this one, the derivative of g. Okay? So that's my brief little explanation, but it might be something you honestly just want to throw in a flashcard and try to memorize. But that's the idea. So basically, plug in the top, plug in the bottom, subtract, and multiply by the derivative of the insides. Okay? All right, let's go ahead and move on. And that'll do it, actually, so we don't need to move on. So hopefully that was helpful, and good luck on your worksheets for this week.